Yeah, today we want to solve one of the questions, spectroscopy question. Alright, so that is that. Now, when you are interpreting any spectra, you have to start by looking at the molecular formula from the mass spec. And from the mass spec, the molecular formula of the compound is given to be C8H7N. Now, after knowing the molecular formula, the next is to calculate the double bond equivalent, or what we call the hydrogen deficiency index, to know the number of double bond. So our double bond equivalent, DBE, is equals to the number of, there are several formulas. Now I'm using one of them. The number of hydrogen that carbon is supposed to take when saturated, 8. Remember the formula of alkane is CnH2n plus 2. So the number of hydrogen is 2n plus 2. So we have 2n plus 2. Remember there's nitrogen in our formula, which means that there should be extra hydrogen, minus the number of hydrogens in the molecular formula, which is 7. Number of hydrogens in the molecular formula, all over 2. So n is the number of carbons, so we have 28 plus 2 plus 1 minus 7, because there are 7 hydrogens on 2. 2 times 8 is 16, 18 plus is 19, so we have 19 minus 7 on 2, and when you compute everything, you have 6. Now when you have your DBE to be 6, 4 stands for benzene. So 6 means that we have benzene, suspected benzene, in our molecular formula, because benzene is 4. Alright, so we have benzene, and this is 4, leaving 2. It's either benzene and 2 double bonds, or a benzene and a triple bond. So these are the possible structures that we are expecting, the possible fragments. A benzene and 2 double bonds, or a benzene and a triple bond in all this. Now, having known this, the next thing is now to move on to what we call the IR spectra. Our IR spectra. That gives us the idea of the functional group in our compound. Moving on to the IR spectra, let me give you a brief summary of the IR spectra, the full flow. Now, the IR spectra is made up of numbers ranging from, I will start from 1,000, but usually start from 400. Some books will start with 667. So we have 1,000 to 1,500, from 1,500 to 200 to 2,000. Sorry, I'm adding 500, 500. From 200 or 2,000 to 2,500. Then from 2,500 to 3,000. Then above that up to, we have 3,500 and we have 4,000. Now watch here. Between 1,500 and 2,000 is what we call the double bond region. Between 1,500 and 2,000 is what we call the double bond region, which means that this is where we can find the C double bond O, C double bond N, and C double bond C. This is what we call the double bond region. The triple bond region is between 2,000 and 2,500, which can be C triple bond N or C triple bond C. So this is a triple bond region. Then between 3,000 is where we find the CH stretches. CH stretches. So let's see now. Now the triple bond region we have between 2,000 to 2,500. Usually, the greater the electronegativity difference, the higher the bond and the higher the number. Nitrogen is more electronegative than carbon, which means that this should appear at a higher number than this. Usually, C triple bond N is around 2,200, while C triple bond C is around 2,100. So having this in mind, let's go back to the IR spectra. Looking at the IR spectra, as you can see, there is a stretch. There is a stretch, and what I can see here is 2,250 at the triple bond region. Remember, we said the triple bond region is between 2,000 to 2,500, and 2,200 is around this range, which means that there's a triple bond. So the IR is telling us that there is a triple bond in the formula, and which means that the 2 double bonds we said it may present is not that, it's rather the triple bond. Now the triple bond here is around 2,251. Remember I told you that C triple bond N is around 2,200, while C triple bond C is around 2100. This is around 2200, so it cannot be C triple bond C, but rather C triple bond N. All right, that is true. Now let's move on to the double bond region. The double bond region. Actually, carbonyls appear around 1725, whilst alkenes appear around 1600. And it's making sense because the electronegativity difference here is higher than that of this, which means the bonds here is stronger than this, and that is why it is appearing at a higher number as compared to the alkene. All right, now when you look at the spectra again, we have a stretch around 1600, and we have about 3 stretches around 1500. This is the characteristic of benzene. Benzene has one stretch at 1600 and around about 2 or 3 stretches around 1500, and these 3 stretches are around 1500. One immediately 1500, the other below 1500. So this is the characteristic of benzene. So from the IR we are able to know that we have a C triple bond N and we have a benzene in our formula. All right, that is okay. So from the IR, we can have we have seen C triple bond N around 2251. Then we have seen a benzene stretch that is 1600, one around 1500, and this is characteristic of benzene. So the IR has confirmed what the DB suggested. We have seen our benzene, we have seen our triple bond. So this is IR, this is the data. The next thing is now to move on to the mass spec. The mass spec. All right, so I am moving on to the mass spec. The mass spec, you can't interpret everything. You need to interpret certain fragments. Watch. Benzene has molecular formula C6H6. When you calculate the molar mass of this, you will end up getting somewhere 78. Usually a fragment around 77, a fragment of 77 is a characteristic of benzene. A fragment of benzene. Why? Because one hydrogen has been break is a fragment, so one hydrogen is not there. That is why it's now 77. So anytime you find a fragment that is 77, just know that it is benzene. But when you have a fragment as 91, then that is benzyl, benzene with a CH2. It's a fragment. Why? Because the whole of this is 77. So we have 77 plus 12 plus 2, that's 14. This is 11, this is 8 plus 1, 9. So a fragment at 91 is suggesting a benzyl. So let's see whether we can see those things in our mass spec. Looking at the mass spec, there is a fragment at 91 and there's a fragment at 77. The 77 is confirming the presence of benzene, and the 91 is telling us that there is a benzyl. That means that a benzene bonded to a CH2. The peak that you see at 117 N plus dot is the molecular ion peak. That is the peak of the molecular formula, the entire molecular formula. All right, so let's see what we can do. From the mass spec, these are the fragments. We have benzene, that is the 77. We have the benzyl, CH2C. So this is the benzene fragment, and this is the benzyl fragment as 91. Mind you, the molecular formula given was C8, H7N. 8 carbons. Let's see. We have gotten how many carbons here? 6 carbons for benzene, 7. And remember the triple bond there from the IR, 8. So the number of carbons that we are looking for is up. Because 1 carbon, 6 plus this, 8. Let's now move on to what we call the IR. So now we know that our structure contains triple bond, a benzyl. Let's move on to the IR. Let me gently clean this portion. Then we move on to the, so this is the mass spec fragment 77 and 91. Take note of those ones. Alright, so we are moving on to the last one, that is the NMR. No? Let's move on to carbon 13. Carbon 13. The C13. The carbon 13, we have several types. We have the depth, we have the proton decoupled. The depth tells us whether there is CH3, a CH2, or a CH. These are the three things that the depth can tell us. That is depth 90 and depth 135. It tells us whether there is this, and this. That is all. But the proton decoupled tells you all carbons, whether it's a carbonyl, a carbon without hydrogen, or it tells you all types of carbons. Let's see what is going to happen from the depth. Now, the depth, if it's CH2, you have what we call an inverted peak. But apart from that, CH3 has upright peak, a CH also has upright peak. Let's see what is in here in our depths. You could see that it is written that carbon 13 spectrum, then depths. Then they kept some arrows there. One arrow points down. Okay. One arrow, they kept depth there, CH2 down. You can see here, here, CH2, then the root down arrow, CH3 up, CH up. Now, the topmost graph is a depth graph, whilst the bottom one is a proton decoupled. It's written there. Sorry, it's not clear. Now you can see that there's an inverted peak here. This is the spectrum, the top one. There's an inverted peak here, and there's also another peak here. So the inverted peak there tells you that there is a CH2 in your compound. Why? Because depth tells you the presence of CH2. And that is agreeing with what mass spectra gave us, that our compound has a benzyl. Do you remember that? Because from the mass spec, we suggested that there's a benzyl there. And truly, the depth has noticed that there's really a CH2 because it gave us inverted peak. So how do you write that? You tell them that from depth, carbon 13, that is the depth, CH2 is present. From the depth, we can see that CH2 is present because there's an inverted peak. Then the other peak, we cannot tell whether it's a CH3 or it's what, we cannot tell. But watch here, let's move on to the proton decoupled. The proton decoupled. The proton decoupled tells you all carbons. You see, there's also another peak just here, which is in line with the depth, what the depth gave you. This is the same CH2. It means what the depth saw is what the proton decoupled also saw. So they are the same. That is why they appear at the same number, the same position. Then when you come here, this is solvent. There's there about 1, 2, 3, 4. 4 peaks in general. There is one just before the. So we have 1 here, then we have 3 here. Let me check it again. 1, 2, 3, 4. Plus is 5. So 5 peaks in general. This tells you that there are 5 different carbons. Remember, we saw a C triple bond end from the IR. So this is one carbon. That could be that's one carbon. The CH2 is another carbon. This is another carbon. This and this are the same. This and this are the same. And this is different. So we have 1, 2, 3, 4, 5. So we have our 5 carbons. So from the depth, from the IR, and from the mass spec, we can conclude that our structure or the molecular formula or the molecular structure is this. Bonded with a CH2, bonded with a C triple bond N. You do not need to interpret everything. We got the benzene from molecular formula, and we suggested either 2 double bond or a triple bond. From the molecular formula, the DBE was 6, which means that a benzene, that is 4, remaining 2. And that 2 can either be 2 double bond or a triple bond. Then we went to the IR and saw that from the IR, there is a peak around 2251. And I told you people that the IR, the peak around 2000 to 2500 is a triple bond side. This bond or this boundary is a triple bond side. And we saw that there was a peak or a stretch there. And that stretch cannot be C triple bond N because it is too high. That stretch was around 2251. And it's around 2200, so that would be for triple bond N. So we got this and the benzene from the IR. Then the depth, we are able to get the CH2. Then from there we combine all things and then our structure is this. So this is a summary. Thank you. Alright, so that is the summary. All the best.